entitled, has my name at the bottom, and it's talking about fluid mechanics, hydraulic engineering, and hydrologic design. The first page looks like this. My telephone number is given at the bottom, and feel free to give me a call anytime. Of course, this is an informal session tonight, so feel free to ask questions, and we'll discuss anything of interest to you and to the group this evening. And then if thoughts come to you as you're working problems and reviewing the material and so forth, just give me a call, and maybe I can help out over some rough points or something that you might want to talk about. I'll be, of course, finishing up the last hour this evening, and then continuing for the next 2 weeks, the full 3 hours next week and week after next. And so tonight we'll be talking about fluid mechanics and talking briefly about fluid properties. You always start fluid mechanics by looking at the basic properties of fluids, and then fluid statics, the fundamentals there, and fluid dynamics. And then next week we'll go into hydrologic engineering, and hydrologic engineering is just applied fluid mechanics, and I'm not sure where you draw the line between fluid mechanics and hydraulic engineering. You'll notice in your book and Michael Lindbergh's civil engineering reference manual that you have, that he goes ahead and includes the pressure conduit hydraulics as part of the fluid mechanics chapter, and I've broken it out as hydraulic engineering, thinking in terms of dividing hydraulics between pressure conduit hydraulics, where you've got the water flowing under some pressure other than atmospheric pressure, and then open channel hydraulics, where you have a free surface at atmospheric pressure. And then you'll note in the slide here that hydraulic structures will fit in next week as well. And then week after next we'll move into hydrologic design, hydrology, engineering hydrology, and look at groundwater hydrology and flow through porous media using Darcy's law, and then briefly looking at flood hydrology, which will include probability and statistics, flood frequency analysis, flood routing, dealing with flood hydrographs and flowing down a stream and through a reservoir and so forth. And then rainfall runoff modeling, the rational method, the unit hydrograph approach that's used in drainage design and so forth, answering the question, how much water should I design the culvert for, or the storm inlet for? And then we'll also look, finish this series of 3 weeks up with water supply hydrology by looking a bit at reservoir firm yield analysis. And so this is where we'll be going in the next couple of weeks, beginning right now. And of course, as Calvin Woods I heard point out, time is limited, and we're hitting the highlights. The book, the materials, the Civil Engineering Reference Manual and associated materials cover things in some degree of detail. The topics that I'm planning for us to cover are also all covered in the book, and then the book will cover some other topics that we're just simply don't have time to get to. I'll try to hit the highlights. And in my mind, the most important thing in preparing for this exam is working problems. That the exam consists of working problems, and hopefully it'll be useful to you for us to review these things in a discussion lecture format. But to really prepare to work problems, you need to work problems. And so the course materials do have lots of example problems, lots of problems that you can work and then check the solutions to. And depending on how much time you've got to devote to this effort, I would suggest the more problems you work, the better off you are. Okay, are we ready to get started? Fluid mechanics is a topic. We're beginning with fluid properties. assuming we're probably a mixed group as far as background in fluid mechanics and hydraulics and hydrology. Probably there's people in the group, or typically would be, that's not seen this type of material since when you were in college, which may have been several years ago, and then maybe others who work with hydraulics and hydrology more frequently. Is that a fair assessment?
We already haven't seen it for a while.
I'm sorry?
That's an accurate assessment.
Okay, real good. Okay, we can talk about some of the properties. The book actually covers more properties than I'm intending to get into, but the very basics that we're going to build upon next week and the week following, we need to be familiar with density and specific weight and related properties, and then viscosity. And when we're talking about density and specific weight, we're dealing with mass per time and a weight per time, or mass per unit volume and a weight per unit volume. And so we got to get the units straight. And we complicate our lives by having different systems of units. And on the exam and in just about any type of reference material, you're subject to either of the alternative unit systems. And the first two systems listed here are my preferences. The SI metric system, where mass is in kilograms and force in newtons, or the British gravitational system, where we're looking at slugs for mass and pounds for force. The civil engineering reference manual that you have tends to sometimes use in the fluid mechanics chapter pound mass and pound force, so that you can and to me that's a little bit confusing, but people use that quite a bit as well. You keep your units straight by remembering back to Newton's second law, or that's the tool I like to use to relate force and mass. And Newton's second law says force is mass times acceleration. And in fluid mechanics, it's more pertinent to think in terms of weight, and weight is mass times acceleration of gravity. And so the difference between weight and mass, in a few minutes, the difference between unit weight and density of a fluid is the weight is the mass times acceleration of gravity, where the acceleration of gravity given here 9.807 meters per second squared, or 32.174 feet per second squared. So using that to define our units, if you're in the SI system, you can define mass in terms of a kilogram, and then the acceleration units are meters per second squared, and then that gives you weight being a newton, and 1 newton is equal to a kilogram times a meter per second squared. If you're working in the British gravitational system, and we can set the pound as our basic unit for force, and having done that and using feet per second squared for the acceleration of gravity units, and then we can define a slug as a pound times second squared per foot. And in the English engineering system, in which you're trying to have pound force equivalent to pound mass, the problem with that, your units are not consistent when you say force is mass times acceleration. And so you've got to throw in a fudge factor, that G sub C in the equation that you're looking at there. And so this G sub C is 32.174 with units foot-pound mass divided by pound force times second squared. And so then you can have your units come out correctly, recognizing that 1 pound force is 1 pound mass times the acceleration of gravity of 32.174 feet per second squared, and then divide by the fudge factor, the 32.174 foot times pound mass divided by pound force times second squared. And so our three systems of units, and you might be faced with working problems in whatever units whoever makes up the exam questions choose to use. Basic properties in fluid mechanics, density and specific weight. We'll be using quite a bit next week. Density is mass per unit volume, and the units are shown here on this sheet, the kilograms per cubic meter, or slugs per cubic feet, or pound mass per cubic feet. And then the unit weight is a weight per unit volume, newtons per cubic meter, or pound per cubic feet. And so the relationship goes back analogously to the force is mass times acceleration, or weight is mass times acceleration of gravity. The unit weight is the density times the acceleration of gravity. Or in the English engineering system, we throw in that same G sub C that we had on the previous page of notes. And I am assuming everyone does have the notes. Was that a correct assumption? We're all got paper copies of what you're seeing on the television screen in front of you?
That's good.
Okay. The properties, including density and unit weight and other properties as well, of course, vary for different fluids, for oil and gas and different gases and water and so forth, but they're also a function of temperature. And often in a problem statement on an exam, they'll not be given a temperature. Of course, if there is a temperature given, you'll want to use that temperature and go to the tables in the reference manual, or the tables that are in the back of just about any of the references that you'll have in fluid mechanics and hydraulics books, and read out the properties as a function of temperature. However, density and specific weight really are not that sensitive to temperature. They don't vary that much, and so at a reasonable temperature that you would expect in engineering situations, we assume if it's not given in the problem statement, maybe something like 10 degrees centigrade or 50 degrees Fahrenheit, gives me this set of numbers here, where I've got density of 1,000 kilograms per cubic meter and a unit weight of 9.80 kilonewtons per cubic meter. And of course, the equivalents in the other units are shown here too. Density is 1.94 slugs per cubic feet, or 62.4 pound mass per cubic feet, and the unit weight is 62.4 pounds per cubic feet and 62.4 pound force per cubic meter. And we can all memorize those numbers. And in the example problems to come later this evening and next week, we can, whenever we have a formula, an expression that has density or unit weight in it, we can pull those numbers out and plug them in. Sometimes we'll express the fluid property in terms of a specific gravity, and by definition, the specific gravity of a fluid is the ratio of the density of that fluid to the density of water at a specified temperature and pressure. Different people can set different standards for that specified temperature and pressure. So the formula in front of you there is the specific gravity is the density of the fluid divided by the density of water. And of course, if you like, you could write it as the unit weight of the fluid divided by the unit weight of the water. Another property that will be expressed in equations and concepts to come later this evening and next week is viscosity. And viscosity is a measure of the property of the fluid, of its resistance to flow. And of course, if you've got a glass of water, you can pour it out quite readily. You might have a little more trouble getting ketchup out of the bottle. Ketchup doesn't flow quite as fast, or molasses. It's much more viscous than water. And some fluids are more viscous than others. Different motor oils have different viscosities. The thickness or the resistance of the fluid to flow. Now, if we want to define that mathematically, we can use Newton's law of viscosity. And for a laminar flow, and if you'll remember your fluid mechanics, laminar versus turbulence. Turbulent flow, there's lots of random motions, but laminar flow, you've got just one layer of the fluid flowing smoothly over the other layer without the random turbulence. And for laminar flow, Newton's second law of viscosity is the shear stress is some constant of proportionality times the velocity gradient. And that constant of proportionality, that by definition is the viscosity. And that's often termed a dynamic or an absolute viscosity. And typically in your fluid mechanics books and in your engineering reference manual, they'll describe the concept by saying that you've got a fixed plate and another plate some distance from it with a fluid in between the plates, and you apply some pressure to the top plate, and you apply a force, and a force per area is that shear stress shown there. And the force that it takes to make the plate move is proportional to the velocity at which it's moving and inversely proportional to the distance between the two plates separated by the fluid. And so that's sort of a classical way of visualizing that. And the units for viscosity are Newton seconds per meter squared or pound second per foot squared. And so you see viscosity in your formulas in fluid mechanics and hydraulics quite frequently, and it's a matter of plugging in that property of the fluid in the expressions. And also you'll see both viscosity and density. And in some cases, a particular formula may have the viscosity divided by the density as a term. And that shows up frequently enough that it's been given a special name of kinematic viscosity. And so for convenience, we define kinematic viscosity as the absolute viscosity divided by the density. And those units will come out, if you take the viscosity units and divide them by the density units, you'll get the result being meter squared per second or foot squared per second. And again, viscosity is a function of temperature. And so you go to your tables in your reference manual or other references that you may be using and look at the properties of water, and they'll be expressed in tabular form as a function of temperature. And I've shown some numbers here for 10 degrees centigrade or 50 degrees Fahrenheit as being typical numbers for engineering problems. And so you can see some numbers here for the absolute and kinematic viscosity. I've noticed in classes sometimes people get mixed up just a bit because the tables are set up. Well, they'll say for kinematic viscosity, for example, they'll say 10 to the 6th meter squared per second at the top of the column. And then you've got to figure out, are we talking about 1.306 there times 10 to the 6th? Or are we talking about 1.306 times 10 to the negative 6th? So that's why you always memorize that viscosity is always a very small number. There's always the negative sign. It's going to be a number times 10 to the negative 5 or negative 6 or negative 3, something of that range. Moving on to fluid statics. And this page of notes lays out the basic concept. This is a fairly simple concept, and it's very fundamental to just about everything related to fluid statics in this expression. And now in fluid statics, we're talking about fluid at rest, no velocity, no movement. And so for a fluid at rest, if you pick a point in the fluid, the pressure is the same in all directions. Viscosity is totally irrelevant. Viscosity doesn't come into play at all. And if you look at a horizontal plane through the fluid, at any point in a horizontal plane, the pressures are going to be the same. And even when we move into fluid dynamics, we often assume for certain analysis hydrostatic pressure distribution. And so the basic concept in this equation, if we've got a container of fluid, let's say it's water or oil or some liquid, and we've got 2 points, point 1 and a point 2, and we want to know the difference in pressure between those points. Pressure is just a vertical height of the column between 2 points times the unit weight of the fluid. And so we're talking about 2 points. We can say pressure 1 minus pressure 2 is the unit weight of the fluid times the difference in elevation between those 2 points. And the difference in elevation we call the head. And so the basic equation here that we see over and over again is the fundamental equation in fluid statics is pressure is the unit weight gamma times the head h. It's just the pressure at a point is just the vertical length of the column of the fluid above that point times the unit weight of the fluid. And often we're looking at forces instead of pressures, and if that's the case, a force is a pressure times an area, which is the next equation given here. And when we talk about pressures in fluids, we've got to keep in mind what we're using as a reference datum from which to measure pressure. And the two common datum is absolute zero, and if you're measuring pressure from absolute zero, we call that absolute pressure. And then much more commonly in engineering applications, we use gauge pressure. And the reference point for gauge pressure is atmospheric pressure. And so the absolute pressure is the gauge pressure plus the atmospheric pressure. And this concept is illustrated schematically here. If you take a point A, for example, on the schematic, point A has a pressure greater than atmospheric pressure, and so we can measure the pressure from the local atmospheric pressure, and that would be the gauge pressure at point A, or we can start from absolute zero and measure the pressure and get the absolute pressure at point A, and of course the gauge pressure plus the atmospheric pressure gives us the absolute pressure at that point. Let's say we're on the suction side of a pump, for example, and that would be an example where you could get a pressure which is less than atmospheric pressure. And so on the suction side of a pump, and we'll look at a problem next week dealing with pumps and the fact that you can get the pump so high and the velocity so high that you can reduce the pressure on the downstream suction side of the pump to something near the absolute zero, and we can talk next week about what that implies. But in this diagram, point B is such a point. It's less than atmospheric pressure, and so the gauge pressure is a negative number. We call that a vacuum. And of course, the absolute pressure will always be a positive number. So in addition to the pressure of working full-time and at the same time trying to prepare for the professional engineer's exam, you've got the pressure of the atmosphere on your shoulders. And the pressure of the atmosphere we ignore in many of our engineering problems and just do the analysis using gauge pressure. But the atmosphere is part of the fluid column as well. Let's see, what's the pressure 10 feet below the surface of a swimming pool? Basic equation that serves as the basis for fluid statics. Pressure is gamma h. The unit weight of the water is 62.4 pounds per cubic feet. The depth, if you're at the bottom of the swimming pool, and it's 10 foot deep, is 10 feet, and so you've got a pressure of 624 pounds per cubic foot. And of course, there's a column of fluid above the surface of the swimming pool, the atmosphere, and I never did say gauge pressure, and in problems on exams and so forth, it's usually not mentioned. We just work the problem the way it's stated here, but recognize that that is a gauge pressure. If we wanted an absolute pressure, we would have to take in consideration that other fluid, the air sitting on top of the surface of the swimming pool. And at standard atmospheric pressure, we'd have another, about 2,100 pounds per cubic feet to add to that. Let's see, this example, we've got a tank of water, And we've got a 3-meter column of gasoline floating on top of the water. And the specific gravity of the gasoline is 0.73. The atmospheric pressure is given as 101 kilopascals, and problems to compute the pressure on the bottom of the tank. And so on the bottom of the tank, it's supporting this column of water, plus this column of gasoline, plus this column of air, the atmospheric pressure above the gasoline. And so for each of those columns of fluid, we multiply the unit weight of the fluid times the vertical height, the gamma h, and add them together. And so we can plug in the numbers into that and determine the pressure at the bottom of the tank. And if we want to work in gauge pressure, and typically that's what we want to do in engineering problems, we would just say the unit weight of the water is 9.81 kilonewtons per cubic meter times the vertical height of the water, which is 2 meters, plus the gasoline. The unit weight of the gasoline is the given specific gravity times the unit weight of water. 0.73 for the specific gravity times the 9.81 kilonewtons per cubic meter for the unit weight of water, and that height of that fluid column is 3 meters. And so we get the 41.1 kilonewtons per meter squared is the gauge pressure, but then we remember there's another fluid on top of the gasoline, and that's the air, and so we want to consider that. If we want to express this as an absolute pressure, we'll need to consider that as well. And so the gauge pressure plus the atmospheric pressure, and we've just computed the 41 kilonewtons per square meter plus the atmospheric pressure of 101 kilonewtons per square meter. That gives us 142 kilonewtons per square meter, and people like to use the term Pascal to express a Newton per meter squared, and so 142 kilopascals. Notice in this problem, if I go back to the diagram, notice the basic concepts we started with, that it doesn't matter what the shape of the container is. We're just talking about the vertical distance. At any point, the pressure is the same in a horizontal plane, and that horizontal plane is irrelevant of whether we're up here where the container is quite narrow or we're down here where the container is much wider. The shape doesn't matter in that regard. And so if we repeat ourselves, express the same concept in the context of a manometer problem. This is another classic fluid mechanics problem of fluid statics that expresses the basic concepts, and then in addition to expressing the basic concept of pressure is gamma times h, this also happens to be a measuring device. Manometer is a device that's used to measure pressures, a very an accurate device at that. And so the figure you're looking at, the diagram is expressing, we've got a pipe, so the circle is a cross-section through a pipe. The problem is to compute the pressure in the pipe. And so we've got a manometer. In any fluid mechanics lab, you'll find manometers hooked up to pipes into other containers of water and other fluids. And you could use any fluid you wanted in the manometer, but we use mercury because it has a very high specific gravity, and so you don't have to have such a high column of mercury like you would have for lighter fluids. And so the pressure is what's making this difference in the height of the mercury here. So the basic concept, if we started from either end, if we started from here, this is where the mercury is at atmospheric pressure. So we know the pressure there, it's atmospheric pressure. So if we were to go down to here, we know the pressure here is the atmospheric pressure plus the difference in pressure between these 2 points. And that difference is pressure times gamma. Gamma is the unit weight of the mercury. The head, the vertical distance, is 2 feet. That would give us the pressure there. Now remember that in fluid statics, that for any horizontal plane, the pressure is the same. So I can jump from there on across to this other point, and the pressure will be the same. Now if I want to come up to here, all I've got to do is recognize that the difference in pressure between this point and that point is just pressure times the unit weight of the water, unit weight of the water times the height, and and the height is 1.5 meters, and then again recognize that in a horizontal plane the pressures are the same, and that takes me to the center of the pipe. And so actually in the solution given here, we started on the opposite end at the pipe, and so all the manometer problems, once you can work one of them, you can work all of them, because there can be any number of different variations of manometer configurations, but the basic concept is to start at a point and track the pressure through and write it as an equation. So let's do that. And so we write our equation. So we look at the center of the pipe here, and we don't know the pressure there. The whole problem is to determine the pressure at this point, so we just write it as the pressure in the pipe, the variable. And then we go through the system. And let's go down to get the pressure at that point. Now that's going to be a greater pressure because we've got 1.5 feet of water causing additional pressure. And that additional pressure is the 1.5 foot H times the unit weight of the water. And we know the unit weight of the water is 62.4 pounds per cubic feet. And that's going to give us a pressure there. And then the pressure there is identical to this point where I come horizontally across. And then when we come up here, we're going to have a decrease in pressure as we go vertically upward. And that decrease in pressure is going to be 2 feet times the unit weight of the fluid, which happens to be mercury. And so the unit weight of mercury is a specific gravity of 13.6 times the unit weight of water, which is 62.4 pounds per cubic foot. And that vertical height of that column of mercury is 2 feet. And so we can plug those numbers in, and that's equal to atmospheric pressure. But we'll take the conventional approach in which we'll do our work in terms of gauge pressure, and atmospheric pressure we'll call zero. That's our reference, so we write the zero, one variable, the pressure in the pipe, and so we solve for the pressure in the pipe of 1,604 pounds per square foot. Okay, everybody okay with that? Well, a little different, but in essence about the same thing. Fluid statics is just applying this basic concept in a lot of different contexts, and forces on submerged surfaces. Now on this page of the notes, you're looking at three related but different approaches for estimating forces. And the first set of formulas are valid if you have a flat surface. And so what we're talking about here, we've got some object, some structure in the fluid, in the water, and the water exerts a force on that container or that object. And if it's a flat, plane surface, you can use these two equations. And we'll do our first example problem with these two equations. And then that example will define the terms here. Notice we'll have a force is equal to the unit weight times the head times the area. Same thing as before. Pressure is gamma times H, unit weight times the vertical height of the fluid column. And then if you want a force is the pressure times an area. It's just that the head this time, the H sub C, is going to be the distance from the, let's say water, whatever fluid, I'll say water is the fluid, the surface of the water to the center of gravity of the plane surface. And the area is the area of the surface over which the fluid is exerting its pressure. And then this gives us the location of the force, and these two length terms, LP and LC, we'll define on the next overhead page of notes, and those will be distances measured along the plane from the water surface to the center of pressure, and from the water surface to the center of gravity. And this will be the moment of inertia, and again the same LC that we just noted times the area. And so those equations will apply in just a moment to our first example. And then having done that, we'll go on to this approach, and these set of equations are good for this plane surface, but they're equally valid for any type of a curved or any type of a configuration of a surface. And in that case, we're using the same formula, except we're applying it to a horizontal projection of the surface. And so the force applied to the horizontal projection is the unit weight gamma times the h sub c again times the area A again, and that'll give us a horizontal component of the force. The vertical component of the force will be the volume of the water above the surface, the structure or whatever object force is being exerted upon, times the unit weight of the water. So that approach will work for either planed or curved surfaces. Now our second example will illustrate those equations. And then buoyant force, we'll define that, and the concept of force is equal to the unit weight of the fluid times the volume displaced we'll use in a third example. Okay, so these are the basic equations, and they can be derived in the fluid mechanics books, and we'll apply each of them in an example. So in this first example, we are dealing with a figure, and it's triangular in shape. So we're just saying there's some sort of a structure. The fluid is water, and so down in the water some distance is this structure that has a triangular shape, and you'll see from the diagram that it's not vertical nor is it horizontal, but it's at an incline, a 45-degree incline, and the dimensions of the object 2 meters across, and then the length from top to bottom is 1.5 meters, and at some distance below the water surface, this point, the bottom of the object, is 2.75 meters below the water surface. And so our problem is to find the magnitude and location of the resultant force. Now the direction of the force is always perpendicular normal to the plane surface when you're dealing with fluid statics. Okay, the formulas from the previous page had some terms in them that we can again redefine looking at the diagram. The L sub C is the distance from the water surface to the center of gravity of the plane surface. The L sub P is the distance from the water surface to the center of pressure, and notice that's measured not vertically but along the incline at which the plane surface is inclined in the water. The H sub C, now that's a vertical measurement, and that's the head, the vertical column of water, and it's measured from the water surface to the center of gravity of the plane surface. And okay, moment of inertia is given here, and you can look at the tables in the different references for the moment of inertia for different types of shapes. For a triangle, it's given here as bh cubed over 36. And so we're basically dealing with a plug the numbers into the equations problem here. And so let's plug the numbers in to compute the force, and then the location of the force. So the equation we've looked at, the force is equal to the unit weight of the water times the H sub C, that vertical head, times the area. And then the distance, we'll use this formula, which also has an area in it, so we'll need to compute the area. And this is just geometry. And leaving fluid mechanics, going to geometry, the area of a triangle is 1/2 the base times the height. Looking at the figure, reading off the dimensions, 1/2 times 2 meters times 1.5 meters gives us our 1.5 meters squared. Now that vertical head, that vertical length of the fluid column, it's measured from the water surface to the center of gravity of the plane surface, and we're given the dimension from the water surface to the bottom of the plane surface, the 2.75 meters. So this is geometry again in trigonometry. The center of gravity is 2/3 of the way from the bottom, and the length is 1.5 meters measured along the incline, and the h sub c is not measured along the incline. It's a vertical height, so we've got to multiply the incline measurement by sine of 45 degrees, and that gives us our h sub c, the 2.043 meters. And then the L sub c is measured along the incline, and so we can take h sub c and divide it by the sine of 45 degrees to get the measurement along the 45 degree incline, which is longer, 2.889 meters. And so those are some of the terms we'll plug into our equation. Another thing we'll need to plug into our equation is the moment of inertia, and so we plug in the base, the width of the triangle is 2 meters, and the height of the triangle is 1.5 meters, and we cube that and divide by 36, and notice the moment of inertia comes out in units of meters to the fourth power, the 0.1875 meters to the fourth power. And so we have all of those values we need to plug into the basic equations now to get the force and the location. So taking our first equation and computing the force by plugging in the unit weight of the water, the 9.8 kilonewtons per cubic meter, that vertical length of the fluid column measured from the water surface to the center of pressure of the plane surface, the 2.043 meters, and then the area of the plane surface of 1.5 square meters, will get a force of 30 kilonewtons per well, I've got a typo there, don't I? We need to fix that. We need to mark out the cubic meters there. That's just 30 kilonewtons. So I just flubbed up and made an error on the notes that we need to correct. So the answer, the force, is 30.0 kilonewtons. That meter and that meter squared cancel out with that cubic meter. And then plugging our numbers in to get the location, L sub p minus L sub c is the moment of inertia, which we determined a value for above, divided by the L sub c, which we computed on the previous page, times the area we computed on the previous page. And so L sub p minus L sub c is 0.0433 meters. And then to get the L sub p, we need to add put the L sub c on the other side of the equal sign, and we'll get 2.932 meters. Now we could take that same pair of equations, or we could take that same example problem and solve it using the same approach that we're about to use in this example problem. And so the approach we're about to do now is applicable to curved surfaces as well as plane surfaces, flat surfaces. And so to illustrate that, we're computing the force exerted on the curved corner by the water. And so we don't have a plane surface, we've got a curved surface, and it's in the shape of a quarter circle. And we're interested in the force exerted on it. And the dimensions are all given here in the diagram, and you can see the configuration and the dimensions we're dealing with. The fluid again is water. And going back to the page of the notes 3 or 4 pages earlier that we looked at, remember the equations look like this. The horizontal component of the force is that same gamma h, the same pressure, times the area again. And except we're applying this now to a projection. And so the h sub c is 11.5 meters. And so if you'll go back to your diagram, I'll not put it on the screen, but it's there in front of you, and I've got a copy in front of me, of course. And the corner, it's 10 meters deep at the top, and the area we're dealing with is a unit width. Well, I will put it back. If we take a look at this again, and we're going into the paper 1 meter, and so the horizontal or the vertical projection here is an area that's 1 meter into the paper, Vertically, it's 3 meters. And so that's 1 times 3, that's 3 meters squared times the area, and then the distance from the water surface to the centroid is the 10 meters plus half of the 3, and that's going to give us 11.5 meters from the water surface vertically to the centroid of the area. And the unit weight of water continues to be 9.8 kilonewtons per cubic meter. And so that gives us a horizontal component of the force of 338 kilonewtons. Now, to get the vertical component of the force, we can just take the volume of the water above the curved surface and multiply that by the unit weight of the water. And so the volume is just a geometry problem of figuring out the geometry of that volume. And so for the top 10 meters, we're 1 meter into the paper. We've got a width there of 3 meters, and we've got 10 meter vertical distance, and so that gives us this part of the volume. And then the curved surface is a quarter circle. So if you take the area of a fourth of a circle and multiply that by 1 meter into the paper in that direction, you'll get that portion of the volume, and then those two components of the volume will add up to the 37.07 cubic meters. And we'll take that volume in cubic meters times the unit weight of the water in kilonewtons per cubic meter to get the vertical component of the force. And then we'll get the resultant force by saying the resultant force is the square root of the horizontal component squared plus the vertical component squared, and we plug in the numbers to get the resultant force. Now the third problem will illustrate the concepts of buoyancy and flotation. And the basic concepts are summarized here. First of all, a body immersed in a fluid is buoyed up by force equal to the weight of the fluid displaced. And secondly, a floating body displaces its own weight of the liquid in which it floats. And so we can illustrate that by this example. And we've got a block of wood floating in water. Now the wood is lighter than the water, so it has a tendency to float. Water, of course, is 62.4 pounds per cubic foot unit weight, and the wood is 40 pounds per cubic foot. And so this particular problem says to compute the force in the rope. And so we've got the block of wood. It's the buoyant force of the water is tending to move the wood upward toward the water surface. The rope's holding it down, and then of course the weight of the wood itself is also holding it down under the force of gravity. And so the force balance is the three forces, or the buoyant force of the water, which is the one we're illustrating and interested in from a fluid statics perspective, but also the weight of the wood and the force in the rope. And in the problem we're solving for the force in the rope. And remember, the basic principle is that the buoyant force is the unit weight of the fluid times the volume displaced. And the unit weight of the fluid, well, we jumped over to English units for this problem, so now it's 62.4 pounds per cubic meter. And you can do the geometry of the block of wood. It's 1 foot wide, 2 feet high, and then the dimension into the board is 1 foot. And so that's going to give you a volume of wood of 2 cubic feet. And so that's also the volume of the water that's displaced by the wood block. And so the buoyant force is 124.8 pounds, and we've done our fluid statics here, and now we need to do the force balance. And so the weight of the wood is 40 pounds per cubic feet times the volume of the wood to get 80 pounds. And so the buoyant force minus the weight of the wood minus the force of the rope's going to be summing to 0. They're in equilibrium. And we know the buoyant force, we know the weight of the wood. The only thing we don't know is the force in the rope, and that's what we solve for to get the 44.8 pounds. Now we can do that all over again using the equations that we used in the previous examples as well. And so in this alternative solution, we're going to compute that same buoyant force on the submerged body as a difference between the vertical component of the pressure force on the underside of the wood block and on the upper side of the wood block. And so here are a couple of equations that we've seen already. And again, back to that original transparency, the pressure is gamma H, force is pressure times area. And so in this context, the H, the head, is measured from the water surface. If we're looking at the force on the top of the block of wood to the top of the block of the wood, if we're looking at the buoyant force on the bottom of the wood, from the water surface to the bottom of the wood. Another way of expressing the same thing in this context is the force is a unit weight times a volume. When we plug in the numbers here, it really doesn't even matter which of these two equations we're plugging into, the numbers are the same. And so we plug in the 62.4 pounds per cubic feet, the H sub C of 5 feet, the area of 1 square foot, and so this is the area of the bottom of the block, and that's the vertical distance from the water surface to the bottom of the block and the unit weight of the fluid. And so that force is lifting the block, sending it upward toward the water surface. But then there's a pressure force on the top of the block as well, and so 1 cubic foot, that's the area of the top of the block. 3 feet, the vertical distance from the water surface to the top of the block, and the unit weight of water continues to be 62.4 pounds per cubic feet to give us the very same 44.8 pounds as we got in the previous solution.
Excuse me.
Yes.
Calculating that out with a calculator came out to 124.8 pounds.
Oh, well, it shouldn't have. It should. You're right, though.
62.4 times 5 times 1.
Yeah, you're right. What are we missing here?
Are we missing the weight of the wood?
No.
If the weight of the wood being 80 pounds, if you program that in, you come out, I think, with 44.8. That's 124.8 minus 80 pounds.
Right.
Oh, okay. Actually, I think this is the right solution. It may be we need to go back and look at the other problem just a moment.
Buoyant force is 124.8. That's what the buoyant force is, isn't it?
Oh, sure.
Not 44.8.
I got it, yes. It's not the force on the rope, that's the buoyant force. Sorry.
You guys are right on target, right on target. Yeah.
How embarrassing.
Yeah, you guys are right on target, and I appreciate that. That is the buoyant force. The buoyant force is 44.8 pounds. That is the correct solution. I'm sorry. The correct solution is these numbers come out correctly, and so whatever they come out to be, which is 2 times 62.4. So what's 2 times 62.4?
124.8 pounds.
Okay. That is the buoyant force. And as someone just pointed out, that is a buoyant force. So what's the 44.8? That's the force in the rope.
Minus the weight of the wood.
Yeah, you're right on target. The 44.8 is the force in the rope, and the 124.8 is the buoyant force, and so we do have to, all we've done here is computed the buoyant force. Everybody straight now? Did I confuse anybody? Thanks for correcting that.
Got some good students there.
That's right. And so all we've computed there is the buoyant force, and so the buoyant force is what it's supposed to, it is 124.8 feet, and what I've written down here is the force in the rope erroneously. And so to get the force in the rope, we need to go ahead and do the rest of the computations that we did in the previous solution. Okay. Tell you what, we've got one more point, and I can make it, I think, in 1 minute. I see it straight up 9 o'clock. But if you can give me 60 seconds, we can wrap things up here. Conservation of mass, conservation of energy, and conservation of momentum are going to be three basic concepts from fluid dynamics, which will continue with us next week in hydraulics. And so conservation of mass, which we call the continuity equation, is just saying that if we're in pressure conduit flow and pipe flow, 2 sections in a pipe. If we're in open channel hydraulics next week, 2 sections in an open channel. And so the mass flow rate is equal to at one section is equal to the mass flow rate at another section, and we can write that as the mass flow rate is the volumetric flow rate, which is the area times the velocity times the density, gives us a mass flow rate. And so the volumetric flow rate at one point, and here's the basic equation we all memorize, the volumetric flow rate, the discharge, is velocity times area, velocity times area, and then times density to convert that to a mass flow rate at the 2 locations are the same, at 2 sections in a pipe, say. For incompressible fluids, and typically in dealing with water, that's what we're dealing with, and most other liquids, the density is constant, and so the rho 1 and the rho 2 drop out, and so when we're in pipe flow, A1 V1 is equal to A2 V2, Q1 is equal to Q2, and then conservation of energy. This is our last page of notes, which we'll end on this evening. Conservation of energy comes from Bernoulli's equation. Bernoulli's equation says total head is elevation head plus pressure head plus velocity head. And so we can say, Bernoulli's equation would say that the total energy at one point is equal, on a streamline, is equal to the total energy at another point. And in hydraulics applications, those 2 points might represent 2 sections in a pipe, or in open channel hydraulics, 2 sections in a channel. Except this is not quite true, because we really don't conserve energy. We lose energy, or at least we lose hydraulic energy, as hydraulic energy is converted to heat and lost to the environment. And so we have a head loss term, and we'll spend quite a bit of time next week dealing with a head loss term. But we can also add energy to the system, and we add energy by pump, and so we have a head added by the pump term. And this is the old workhorse of hydraulics, which will be quite useful to us next week. And we won't use it quite as much, but we'll also use the conservation of momentum equation, which I've written here in terms of the impulse momentum equation. The sum of the forces is the density times the flow rate times the velocity vector out minus the velocity vector in. And so these will be concepts that we'll apply in practical problems next week when we deal with hydraulic engineering. And I'm going to stop there and see if you have other comments or questions or anything you'd like to discuss. Well, thank you for your patience. I know 3 hours is a long time to be digesting material after a full day at work, and thank you very much for your patience.